Just during the course of this lecture, I'm going to say a little bit, but not too much, about the use of genetic testing to diagnose inherited disorders in embryos. I'll talk about how we sample the material from the embryo. And then I'm really going to concentrate on how genetic tests can potentially improve the success rates of fertility treatments, specifically in vitro fertilization. I'll talk about some of the clinical data that we've seen using some of these methodologies, and finish up by talking about maybe where we could go in the future with this kind of approach. So the whole idea of testing embryos, human embryos, for inherited conditions is more than a quarter of a century old now. The first clinical cases more than 25 years ago. And originally it was really conceived as an alternative for prenatal testing for patients who already knew they were at very high risk of transmitting an inherited condition to their children. In order to use PGD, this genetic testing, the patients have to go through IVF, even if they're completely fertile. And the way that it works is something like this. You have the ovarian stimulation, which should result in the production of several eggs. Those eggs are then fertilized with the partner's sperm, which should hopefully produce several embryos. Each of those embryos would have traditionally just one cell removed, usually when they're about 3 days old. And a test is done, and hopefully some unaffected embryos are identified, and they're then transferred to the patient in the hope of producing an unaffected pregnancy. It's a very quick process. The day of egg collection is usually termed day 0. The embryos have already been produced by day 1, that's fertilization, and then it's either 3 days after fertilization or sometimes 5 days after fertilization that some cells are removed and then tested. The tests traditionally only take about 24 hours, allowing the embryo to be then transferred within the same cycle of the patient. However, what we've seen in the last maybe 5 years is an increasing trend towards freezing the embryos after the cell has been biopsied, which certainly takes a lot of pressure off the genetics lab. It gives us a little bit more time. I'll show you a picture or a little film of how this kind of testing on day 5 usually works. Here you've got the embryo. You can see the membrane around it called the zona pellucida. That's present in the egg and remains in place until the blastocyst stage, which is what we see here, where you can see the embryo is beginning to emerge from within this membrane, the process that we call hatching. So if you looked at this embryo again in a few hours, the whole embryo would have come out and you just have an empty zona pellucida left behind. But this is the ideal time to capture some of the cells for testing, which I'll show you now. So here we see a closer view. You can see these cells of the trophectoderm around the edge. The embryo at the blastocyst stage, of course, has formed a fluid-filled cavity. Well, let's pause. Set that going again. Okay. So the embryologist is pulling on these cells with a suction and also using a laser to hit the cell junctions to separate off a piece of tissue, which will then be taken away and subjected to genetic testing. So it looks like quite an invasive, hard procedure on the embryo. But actually embryos at the blastocyst stage are extremely robust and they tolerate this kind of insult very well. So there's the tissue removed, there's the embryo. It looks a little sad, but it's actually okay, I promise you. And there's the piece of tissue. So usually you get maybe about 5 cells. Now that in PGD, we're used to testing just 1 cell. So nowadays, when we're getting 5 or maybe even 10 cells, it's a luxury of DNA. And so the tests we have tend to work even better with this sort of approach. So the tissue is removed, genetic analysis is undertaken, hopefully you transfer an unaffected embryo, and of course the whole benefit of this is that the patient begins day 1 of their pregnancy knowing that the fetus will be unaffected and they will not have to contemplate a pregnancy termination. And this is why so many of our patients requesting PGD are actually perfectly fertile, and they choose to go through IVF with all of its uncertainties and discomforts purely because they want to avoid the whole notion of an affected pregnancy. There's been this kind of diagnosis done for more than 300 different inherited conditions, and really since the sequencing of the human genome, more than a decade ago now, it's possible to do PGD for really any inherited condition for which the genetic basis is understood. In the UK, this is tightly regulated, and in most European countries, it's the same also. Tests are very accurate, typically at least 99% has been our experience, and results are usually available within 24 hours, although if the embryos are being frozen, of course, you can take a little longer. I want to put that to one side now and talk about how these kinds of genetic technologies could be used not for patients who have a familial problem to avoid, but just for regular infertile couples having IVF in order to obtain a pregnancy. And this has actually become the greatest, most widespread use of genetic testing applied to embryos. So why would you need to use it? Well, I'm sure you're all aware that IVF is an incredibly successful medical intervention. There's more than 5 million, probably more than 6 million babies born now using these technologies around the world. And in fact, in industrialized countries, IVF is responsible for between 1% and about 4% of all births. So if you go into any classroom in any school, you're likely to find at least one IVF child in that class, and maybe more. So on the surface of it, incredible success, but all of us in the IVF field acknowledge that despite these successes, despite the fact that we've had this technology for more than 3.5 decades, it's still very inefficient. Most IVF cycles do not result in a pregnancy. In fact, if you put together all the patients all around the world, it's only about 1/3 of IVF cycles that produce a baby. There's many reasons for this, but one of the reasons is that we're not very good at identifying which of the embryos produced is the one with the greatest probability of forming a baby. As we talked about already, several eggs produce, several embryos produce, but they do not all have an equal chance of producing a viable pregnancy. In fact, most of them have no chance at all. And so how do you decide which embryo to transfer to your patient? In all the IVF clinics all around the world, the primary way this is done is based on embryo morphology, the beauty contest for the embryo, which one looks the best. And this is not without some value, but all embryologists will tell you that it's a very imperfect guide. Very often you will have a patient with 2 beautiful embryos, perfect appearance, and you transfer them, no pregnancy. And on the very same day, you may have a patient with 2 very poor-looking embryos, but she has nothing else. So you transfer them, and she has twins. So morphology is a guide, but a poor one. And as a result of that, 85% of the embryos transferred in IVF ultimately do not implant and make a viable gestation. In the past, the solution to this is, if you don't know which embryo is viable, transfer them all. Then you will definitely have transferred the most viable embryo. But of course, you all know the other problem with this. Sometimes there is more than one viable embryo. And so you can have a patient with twins. Okay, maybe this isn't so bad. Or triplets, or quadruplets. Many of our infertile patients are quite happy if they get twins because they've struggled to have a family and now they have a ready-made family with 2 children. But the medical reality is that twin pregnancies are at significantly elevated risks of a whole range of problems: cerebral palsy, extreme prematurity, maternal hemorrhage, all sorts of things. And so it's acknowledged today that really the ideal outcome of IVF is 1 embryo transferred, 1 healthy pregnancy. Even though we know this, it's still the case today that about 1/4 of all IVF cycles are twin pregnancies. So even though we know these problems, we're still very tempted to transfer more than 1 embryo to support the pregnancy rate. So if we want to be able to do elective single embryo transfer and always transfer 1 embryo, we better be sure that the embryo we transfer is the one that has the best potential for making a healthy pregnancy. And the question has been, can genetics help us here? Morphology does not do the trick, so maybe genetics could. And there's some very good reasons for thinking it might. We've already heard something about chromosome abnormalities in embryos. Well, it turns out that these abnormalities are extraordinarily common in human embryos. It's an order of magnitude higher in human pre-implantation embryos than any other species that we have good data for. This graph shows you the instance of chromosome abnormality, aneuploidy, in human blastocysts. So these are the embryos about 5 days old, against the age of the mother, and I apologize, these numbers are a little small, but what this is showing you is that, as you know already, the abnormality rate increases greatly with age. Of course, it's the same trend that you see with Down syndrome with age, which is, of course, a chromosome abnormality too. What you can see is that for patients over the age of 40, about 3/4 of the embryos are chromosomally abnormal. So this is obviously a problem. But look, even the young patients, these are patients who are in their 20s, more than 1/4 of the embryos are already abnormal, even at this early age. So it's an extremely common problem. What is the impact of this? Well, aneuploidy is almost invariably lethal to the embryo. Most of these embryos simply won't implant. A few will and then miscarry, and very few will actually form ongoing pregnancies with a chromosome abnormality. So as the aneuploidy rate goes up, the implantation rate, the chance that an embryo forms a pregnancy, goes down. And as you can see, these two lines are like a mirror image of each other. And of course, this is no coincidence. This is because one thing is causing the other. Aneuploidy is causing the implantation failure. So the idea of genetics applied to embryo selection, something that's been termed pre-implantation genetic screening, or PGS, is that you begin with a set of embryos, maybe half or more could be chromosomally abnormal. And rather than transferring one of these without knowing whether it has an abnormality, why not do a genetic test which allows you to differentiate the embryos which are aneuploid and those which are euploid, making sure that you transfer a chromosomally normal embryo. It's not going to guarantee that you have a viable pregnancy, but it will eliminate what is almost certainly the single biggest factor in embryo implantation failure in human IVF. It's well established, many different methods now for looking at all of the chromosomes. This particular one is microarray comparative genomic hybridization. There's also very good quantitative PCR methods, and these days mostly we're doing this with next generation sequencing, which works very nicely as well. What you can see here is essentially all the chromosomes are being tested at multiple points along their length. Each one of these dots is essentially a different test, and if they fall in this middle area, then there's the normal 2 copies of the chromosome. But you can see that this embryo actually has too little chromosome 1 and also chromosome 14. Monosomy 1, monosomy 14. You would never see this in a prenatal sample. You will never see this in a miscarriage, because these are so lethal, these kinds of abnormality, that this embryo would almost certainly not implant. Yet these abnormalities are very common at pre-implantation stages. So I think you'll agree that the concept of PGS seems reasonable. It really is true that we have a large proportion of abnormal embryos produced by patients undergoing IVF. And it really is true that those abnormalities are usually lethal. So surely PGS should work. Well, if you've followed this field at all, you'll know that actually about 10 randomized controlled trials were done a few years ago. And the surprising results of those trials was that none of them showed any benefit of doing PGS. In fact, very worryingly, a couple of them suggested that their patients may have lower pregnancy rates after PGS, presumably because of damage done to the embryo when the cells were removed. So the whole field became very controversial, and there was a lot of debate that went on over several years and is still going on to some extent today. However, the key thing is that all of those trials were done with technologies which would be considered utterly obsolete today. They were only capable of looking at about 1/3 of the chromosomes in each embryo. So not all the chromosomes were assessed. All of the embryos were tested at the cleavage stage, when they were only made of about 8 cells and you could only take 1 away. Nowadays, the testing is done at the blastocyst stage, a much more robust embryonic stage where you can take more cells and get a more accurate genetic test. And it's done using methodologies such as I showed, which look at all of the chromosomes. So the technology has moved utterly from where it used to be. So what data do we have using these modern approaches? Well, the new methods have been shown in several different studies to be very accurate. Typically, the aneuploidy diagnostic accuracy is at least 98%. They're highly predictive. Studies have shown that if you do transfer an embryo that you diagnose abnormal, it very, very rarely will produce an ongoing pregnancy. There have now been several randomized controlled trials using these different methods. I'm aware of 5, although I think only 3 have had proper peer review at this point. Every single one of them has shown an advantage in terms of IVF successes using these kind of approaches. None have reported any negative findings. I don't have time to mention them all, but I'll just quickly mention a couple of them. Here's one randomized controlled trial. Essentially, they're testing at the blastocyst stage and then transferring one embryo. The key thing to look at here is the ongoing pregnancy rate. So when they transfer one embryo in their control group, this is embryo transferred based on morphology, not based on chromosome screening, they get about a 42% pregnancy rate. But in the cycles where the embryo was chosen based on chromosome analysis, they have almost a 70% pregnancy rate. Another study, this one looking at a wider range of IVF patients. What you see here is the delivery rate up to about 85% after chromosome screening versus about 68% in the control group. Important thing to note, this is not single embryo transfer, so they're often transferring more than one embryo. If you want to know what the success rate is transferring one embryo, look at the implantation rate. So this is the sort of pregnancy rate per embryo, and again, it's significantly higher after PGS. The final study, I think very important one, what they did in this case is they randomized their patients into 2 groups. One group had 2 embryos transferred based on their appearance, so traditional kind of way of selecting embryos. The other group had 1 embryo transferred based on the results of chromosome analysis. So this group are having only half the number of embryos transferred as this group. But the pregnancy rate they found was not significantly different between the 2 groups. So essentially they're getting the same pregnancy rate with half the number of embryos. And very importantly, what about the rate of twins? 0 when they were only transferring 1 embryo versus more than half of the cycles where they transferred 2 embryos, they got a twin pregnancy. So this really shows that this kind of approach can guide you to the most viable embryos, allowing you to transfer just 1 and reduce the risk of twins and get the same kind of pregnancy rates. The majority of miscarriages, of course, both in IVF but also in natural conception, are caused by chromosome abnormalities, probably about 3/4 of them, in fact. And of course, that again goes up greatly with advancing age. As more of the eggs have abnormalities, more of the embryos have abnormalities, and then you get more miscarriages. That's what's shown by this blue bar here. These are actual results from thousands of IVF cycles showing the increase in miscarriage with advancing maternal age. So you can see for these older patients, not only is it hard for you to get them pregnant using IVF to begin with, but it's also hard for them to maintain those pregnancies to term. About 1/3 of the pregnancies being lost after the age of 40. If you do PGS, what you find is that the miscarriage rate does not change with age. You've taken chromosomes out of the equation, and what's left behind are miscarriages due to uterine abnormalities, coagulation problems, immunological factors. Around about 7% miscarriage rate, regardless of age. Similarly, the red bar shows that decline in implantation rates that I showed you earlier, this precipitous drop in implantation with advancing age. Again, if you do PGS, what you find is that the implantation rate is almost unchanged with age. In other words, a chromosomally normal embryo from a 42-year-old patient has about the same chance of making a baby as a chromosomally normal embryo from a 22-year-old patient. The difficulty is finding such embryos. One thing that PGS is not is a way of repairing problems. It's just a way of selecting embryos, at looking at them and understanding them a little better. It cannot make viable embryos appear. And so the problem that we have in these older groups is that often we screen their embryos and find that none of them are normal, and so they get no transfer. So I'm not suggesting that PGS solves the maternal aging problem in IVF. It doesn't. Maybe it helps a little. So what can we conclude about PGS? What can it offer? Well, I think we now have really good evidence, including from randomized studies, that PGS can achieve a very high efficiency elective single embryo transfer. Critically, this can give you a faster time to pregnancy. Now, for those of you who don't work in the IVF field, this may be a concept that is new, but it's very important in IVF. Imagine a patient who is already of what we would think of as advanced reproductive age, so maybe 40 years of age. Remember, the chances of pregnancy are going down fast at this time. If she produces 8 embryos, maybe you will transfer 2 and you'll freeze the other 6. But what if she doesn't get pregnant? So some time needs to go by before you thaw 2 more embryos and you transfer them. She still doesn't get pregnant. More time passes, you thaw out 2 more embryos and you transfer them. The patient becomes pregnant, she's really happy. But then maybe 2 months later she miscarries due to a chromosome abnormality, and we've seen how common that outcome will be in patients of 40. So even more time has to pass while you deal with the consequences of the miscarriage before you thaw the final 2 embryos and you transfer them, and she doesn't get pregnant. By this time, your patient could be approaching 42 years of age. All the time that you've been doing these transfers, her likelihood of success in IVF using her own eggs has been going down like this. So she's now faced, age 42, with this decision. Should she do IVF again using her own eggs, knowing that now her success rate is probably 5% or less? Should she go for egg donation, or should she give up on IVF altogether? If you had done PGS, you could probably have told her on day 1 that all of the embryos produced in that cycle had been abnormal. You would have saved her from 4 embryo transfers with all the stress, both emotional and financial, of these procedures. You would have saved her from a miscarriage. And you would have given her a year and a half or maybe longer of time to decide about what she wanted to do reproductively. Would she like to try IVF again using her own eggs while she still has some reproductive potential? So this is very important. We shouldn't forget that embryo transfers are a medical procedure that patients are being subjected to. It's not trivial. Why are we continually transferring aneuploid embryos to our patients that will never make a baby? It doesn't need to happen anymore. The other issue is cryopreservation. As you probably know, there's more than 1 million embryos frozen around the world, and it's a little bit of a dilemma ethically about what to do with these. I can guarantee to you that more than half of all of those frozen embryos are aneuploid and will never make a baby. So this gives 2 questions. Firstly, why are our patients paying for the storage of these embryos which will never give them the child that they may want? And secondly, what about the patient who had an IVF baby when they were 33 and they've still got 2 embryos frozen from that cycle? They want another baby and they're approaching 40, but they're in no hurry to have IVF again because of the 2 frozen embryos. They feel like they have some kind of guarantee of future fertility, these nice young embryos. But if those embryos are aneuploid, and they often will be, the patient has no guarantee of a future pregnancy from those embryos and should actually be thinking about another IVF cycle as soon as possible if they want to have their own biological child again in the future. So it's about providing information to patients as well. Of course, we've already talked about reducing miscarriage rate and Down syndrome, so I won't talk about that any longer. I'll just finish up by just mentioning a couple of future perspectives. In the United States, the uptake and utilization of PGS has grown massively in the last few years. I've only got up to 2013 here, but we expect that this year about 20% of all IVF cycles in the United States will have PGS. In Europe, it's fewer than 5% of cycles. And yes, it's maybe creeping up a little bit, but very, very slowly indeed. So why is this? Are we waiting for more data in Europe, a few more randomized controlled trials, a couple of meta-analyses, Cochrane review perhaps? I don't know. I think certainly we are by nature more cautious than our American colleagues, that's true. And of course, when they get it right, it's great for them because they're miles ahead of us. When they get it wrong, it's a huge disaster because they've got into it too deeply. So I'm not saying that that's a criticism for us. Maybe it's good that we're cautious. I think perhaps a bigger problem is the price of PGS. Now, PGS costs no more in Europe than it does in America. It costs roughly the same amount. But IVF is so much more expensive in America that PGS ends up representing what seems relatively a small add-on, whereas in Europe it seems like quite a large add-on. So particularly the better prognosis patients are probably not going to be so keen when they think they've got quite a good chance of a pregnancy anyway. Will they really go for PGS? So I think it's very important that we do give our patients access to this technology, which I'm convinced is beneficial to them and they should be having. But to do this, we've got to be able to offer it to them at a lower cost. So that's been one of the major research themes of my laboratory, is how you can push down these costs. And we are making progress. In the last year alone, we've managed to reduce our PGS costs by a quarter. And that, I hope, is going to continue. We've got some plans which I think could easily halve the cost of what we have to charge at the moment. So this is mostly based on next generation sequencing, which I won't go into, but of course we've heard something about already. So to mention that we are making progress there. The other area is, can we extract more information? We've got the cell from the embryo, we've got its DNA. What more can we learn? Chromosome abnormalities don't explain all the failures. In fact, if you look at a 35-year-old patient having blastocyst transferred, and you don't do any genetics, you just transfer one of the embryos, you've probably got about a 40% chance that by luck the embryo you transferred was viable, because about 40% of them are capable of making a baby. If you do PGS, you'll find about a third of them are chromosomally abnormal. Now, you're not going to transfer any of them, and so now you're just choosing out of this group. So automatically, your chances of picking correctly goes from 40% up to over 60%. And that's what we see in real life as well. When doing PGS, the pregnancy rates tend to be about 65%. But that still leaves this unknown. You know, these embryos are chromosomally normal. They look okay. Why didn't they make a baby? We don't know. So can genetics tell us something about these two? And our recent data suggests that it may well do. What we've found is that of the chromosomally normal embryos that fail to implant, maybe about a quarter of them have unusual levels of mitochondrial DNA. And we just recently published this in PLOS Genetics. It seems to us that this may explain about a third of chromosomally normal embryo failures. Here's just some of the data. This is the actual amount of mitochondrial DNA. And these ones made a pregnancy, these ones didn't. And you can see really, if you fall into this red zone, the probability of making a pregnancy is extremely low. All of these embryos are chromosomally normal. So, probably, if we do this kind of selection, you can eliminate another maybe up to about 10% of these embryos. And again, that should allow you to boost your chances of picking a viable embryo. So just to finish, I think really the key point I want to leave you with is that we've got really good evidence that genetics can help us in many aspects of IVF. And I think we are going to see it becoming a more and more routine part of IVF treatment. We've seen such advances and such fantastic data coming out. Has the use of genetics in IVF reached the heights that it's going to? Has it reached its zenith? I think no. I think really actually the best is still to come from this. And so the methods will become cheaper and we're going to be able to diagnose viable embryos with greater certainty. So I'll leave it there just to acknowledge that most of the clinical data I was showing was generated by the different reprogenetics labs around the world. And thank you for your attention.